In section 6.2, we're going to look at orthogonal sets and orthogonal bases, as well as orthonormal sets and orthonormal matrices. So we say we have a set of vectors is orthogonal if each pair of distinct vectors is orthogonal. Let's consider this three-dimensional plane where we have x1, x2, and x3. Okay? And so in 3 dimensions, what does it mean to be orthogonal? So if we look at each of these vectors in this set, of course, each of them are distinctly orthogonal. And we can check this by multiplying, say, v1 by v2 and making sure we get 0, v2 by v3, as well as v1 by v2. And not multiplying, I am so sorry, taking the dot product. So now let's look at an example that's not so intuitive, like our three-dimensional space with x1, x2, and x3. So if we have 3 vectors, v1, v2, and v3, how can we show that this set is orthogonal? We first want to start off by finding the dot product of v1 and v2. And we see here that we'll have 0 plus 4 plus negative 4 plus 0, which clearly gives us 0. And likewise, we can show that v2, the dot product of v2 and v3 is also 0. And then we want to do v1 with v3. And we get 0. So therefore, since all of the vectors are orthogonal to each other, we say we have an orthogonal set. So now we have a theorem for orthogonal sets. If S is an orthogonal set of non-zero vectors in Rn, then 1, we can say that S is linearly independent, and 2, we can also say that S is a basis for a subspace spanned by S. We're now going to look at a proof of this to show that the S vectors are linearly independent. Let's look at this proof. So first, let's let the set S be the vectors v1, v2 through vp. And this is an orthogonal set. Okay? And so if we have this linear combination here, c1 v1 plus c2 v2 plus cp vp is equal to the 0 vector. First, if we multiply each side by the, not multiply, take the dot product, of each side. If we take the dot product of each side by the vector v1. Okay? Since these are orthogonal sets, we know that this will be equal to 0. So what do we have? We have this linear combination here times v1 is equal to 0. Now, taking the dot product, using our properties, we can have that c1 v1, and we take the dot product with v1, and then we have cp vp, and we take the dot product with, should be v1. Okay, and so now, our properties tell us that we can take our scalar c1 out, and we'll have the vector v1 dot v1 plus c2 times the vector v2 dot v1 up to we can take our last scalar cp out, and it'll be vp dot v1. Now, what do we know about these dot products here? Since the set is orthogonal, we know that these are equal to 0. So all of the terms from here, from C2 to CP, will give us 0. And this implies that we're left with C1 times V1 dot V1 equals 0. Now, since each of these vectors are non-zero, then this product here, V1, V1, will not equal to 0. And since it cannot equal to 0, that implies that the scalar C1 must equal 0. And so we can do a similar analysis for C2, C3, and through CP by multiplying its corresponding vector V1, V2 up to VP on each, taking the dot product on each side, and therefore we see that the set S is linearly independent. Now, let's consider orthogonal bases. An orthogonal basis is a basis that is also an orthogonal set. And so if we consider the standard basis for R3, which we saw earlier, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so we notice that this is an orthogonal set, and it also forms a basis. So now I want to use the inner product to find a linear combination. And so we'll see that these orthogonal bases are much nicer than the other bases we've looked at, and because we can actually find the weights of the linear combination easily. So we have a theorem that says let S be the set V1 through Vn, an orthogonal set of non-zero vectors. If U is in the span of S, then we have this linear combination U is equal to C1 V1 plus C2 V2 from C plus dot 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 plus Cn Vn. Then we will show that the weights C1, this should not be a vector, sorry ladies, here, is equal to U, the vector U times Vi, the vector Vi, all over the dot, and I'm saying times, and I should be saying the inner product, all over the inner product of Vi, Vi. And so now we'll see a proof of this. So we have U, the vector U, equal to this linear combination here. If we do a similar analysis like we did last time doing the inner product of V1, then from last time we noticed that all of these vectors here, of course, since they are orthogonal, became 0. So we're just left with the vector U1, V1 is equal to C1 times the dot product of V1 here. And so since we know this cannot be equal to 0, then we get that we can easily solve for C1, and we get this U1 dot product, inner product with V1 over the dot product of V1, V1. And so we can generalize this for the case. We can do this for each of the vectors and scalars. And so going from I is equal to 2 through P, we get the general form here to find the weights of the linear combination. So, given these vectors here, V1, V2, and V3, we want to show that this is an orthogonal basis for R3. Then, we want to write U as a linear combination of these vectors, V1, V2, and V3. So, for your reading assignment, I would like you to first show that V1, V2 is an orthogonal basis. How do we do that? Again, we have to show that V1 dot with V2 is 0, V2 dot with V3 is 0, as well as V1 dot V3 is 0. So for your reading assignment, we would like for you to do the first part of this. And now we're going to look at writing U as a linear combination of these vectors. So to find the weights, again, we say this can easily be done. If we want to find C1, we take the inner product of U and V over the inner product of V with V. And so what do we have here? We would have 12 plus 18 over 1 plus 4 plus 9, which gives us 42 over 14, which equals 3. So our weight C1 would be equal to 3. Likewise, we can find C2 and C3. Doing the math, we get C2 is equal to -2 and C3 is equal to 7. You will want to go through this on your own to make sure my math is correct. And then we can form our linear combination of U by using our C1, C2, and C3. So we have the vector U is equal to 3v1 minus 2v2 plus 7v3. So if we have a set of vectors U1 through UP, we call this an orthonormal set if it is a set of orthogonals, it's an orthogonal set, as well as the lengths all have measure 1. And so orthogonal sets, so please excuse me, so if an orthonormal set of vectors span a subspace W, then we say that it forms an orthonormal basis. So now let's look at what we call an orthonormal matrix. Okay. We have a theorem that says a matrix A is an orthonormal if the have orthonormal columns if and only if when I take A transpose and multiply by A, I get the identity matrix. So let's consider this example here where A is equal to the given matrix. Okay. If we look at this, each of these columns say V1, V2, and V3. If we wanted to see if it were an orthonormal set, we would first have to find out if each of these are orthogonal to each other. So we would have to do the inner product of V1 with V2 and make sure it equals 0. And then V2 with V3 and make sure it equals 0. And then V3 with V1, and make sure it is equal to 0. But we also have to consider for it to be orthonormal that it has length 1. So we would have to do the inner product of V1 and V1, and let's just see what happens. We'll have 1 over the square root of 2 to be squared plus 1 over the square root of 2 to be squared plus 0. So we would get 1/2 plus 1/2 plus 0. So indeed, this equals 1. Likewise, V2 dot V2 would equal 1, and V3 dot V3 would equal 1. That should be a 1. So we can go through that to say that this is an orthonormal set, but if we have a matrix, we can just use this theorem and see if this is true. So if we have A transpose times A, we should get the identity matrix. So let's see what happens. So doing this, we take A transpose, and again, the transpose, that means our rows become our columns, times the given matrix A. And so we want this to equal the identity matrix. So let's do only the first operations. We'll have 1 square root of 2 times 1 square root of 2. So we have 1/2 plus, here would be 1/2 plus 0. So we get the 1 vector, a 1 entry here. And if you go through and do likewise, you'll get 0, 0, 0, 1, 0, and 0, 0, 1. And so I would like for you to do this on your own. And indeed, this is the identity matrix. So we can say that this matrix is orthonormal. So lastly, for your second question of the reading assignment, I would like for you to do this example that says, show that the identity matrix in R3 is an orthonormal matrix. So what are we doing? We're showing that I3, which is 1, 0, 0, 0, 1, 0, and 0, 0, 0, is orthonormal. And you may use the theorem from the previous slide to do this.